Hello, let's look through some example problems for properties of functions. So we're first given this function f of x is equal to the 8th root of x plus 8 divided by x squared minus x minus 30. And we want to classify this function as a polynomial function, a rational function, or a root function. We want to be able to explain why with words. So the important thing to notice is that we have an overarching structure here that is this root function at the very end. And so even though we have within it actually a very legitimate rational function, and that rational function is because we have a polynomial here, x plus 8 is a linear function, and linear function works as a polynomial because all we're dealing with are shapes, right? X is a rectangle, 8 means 8 unit blocks, and even below that we have this x square and this minus x and minus 30, and x square is obviously a square, and the minus x and minus 30 are shapes just like the one on the top. So we have polynomials that are turned into a rational function because they have this division bar between them, and then they have that 8th power root on the very end. So we would call this a root function, and we could say because there is an 8th root as the external structure. Now what we'll learn is there's actually some even more formal language we could use here, which is that all of the stuff in the inside is actually composed into an 8th root. So that's another way that you could say it, is you could say that we could say because the x plus 8 over x squared minus x minus 30 is composed into an 8th root. 8th root. Finding the domain, well, the important thing with domain is to keep track of when could we potentially have an error occur by plugging in a value. And as we just said, we have polynomials, and polynomials have no restriction on their domain. There's nothing you can't square, there's nothing you can't multiply by, there's nothing you can't subtract or add numbers to. So really the only problem that we have is going to be if the denominator is equal to 0, that's going to be x squared minus x minus 30 is equal to 0. That could potentially be a problem. And then we also want to be careful of this 8th root, because an 8th root is an even root, and even roots cannot process negative numbers. Because after you multiply by something an even number of times, like you could think of, for example, if I wanted to square root -2, that's a conversation saying what times itself gets me -2. And you can't multiply anything by itself to produce a negative. So for the same reason, 8th roots here will not be able to have a negative on the inside because that doesn't answer the question of what times itself 8 times gets me a negative. There's not a value. If you try positives, they'll stay positive when you multiply them by themselves. And if there's negatives, the 8 amount of those is going to cause all the negatives to cancel away evenly. So everything on the inside here actually needs to be non-negative. So that would be x squared minus x minus 30 has to be greater than or equal to 0. So let's do a little bit of processing. If we do our rectangle method of factoring over here, this is going to be an x squared is going to go in one corner, we'll put the minus 30 in the other corner, and if we think about numbers that multiply to -30 and add to -1, that'll get us -6x and 5x, and we can factor from there. This would be an x, then we would have another x down here, this would be a -6, and this would be a 5, so all in all we could represent this as x minus 6 times x plus 5. This is just a visual way of representing what's normally referred to as the AC method. But after you solve this out, that would be x minus 6 could not be equal to 0, and x plus 5 could not be equal to 0, which means that x cannot be equal to 6, and x cannot be equal to -5. So those are two numbers right there. And then for this next one, we want to be looking again at some of these values where I need to be greater than or equal to 0. Well, the way I like to think about these types of problems is I like to figure out when are the values that cause the numerator to switch from positive to negative, and what are the values that cause the denominator to switch from positive to negative. Because when you have a fraction, if the top is positive and the bottom is positive, then it's positive, but if either of them is negative, it switches over, and if both of them are negative, it stays positive. So we can actually graph all of this on a number line and recognize that the top is going to switch over from positive to negative when x is equal to -8. That's its boundary point. So we'll put a -8 on the line, and we already know when the denominator gets to 0 because that's the 6 and -5 we found before. So I'll put -5 and 6, And then since these are the values when we switch from positive to negative, everything on the inside between them must be either positive or negative. So we can just try some very quick values in our calculator. For example, we can try -9, and if we plug that in, it looks like the numerator is going to be negative. The denominator is going to be, let's see, negative when we plug in for that x minus 6. That would make that negative, and then the next one would also be negative, so the bottom would in total be positive. So we have a negative on top, positive on the bottom. That's going to be a negative right here. All right, what about at -8? At -8, that would be when the numerator switches over, but if we plug into the denominator will still be positive. So that's going to be now, let's see, positive, because it'll be a positive over a positive. Then we can look at values between -5 and 6. I'm going to try plugging in 0, and if I plug in 0, we'll get 0 plus 8 on the numerator is 8. 0 minus 30 on the denominator gives us 8 over -30, so that's going to be a negative value. And then if we look at above 6, we could say, okay, what about above 6? That's going to be a positive number on the denominator, a positive number on the numerator, so that's going to be a positive there. So after we've done this full exploration, we realize that this thing has to be greater than or equal to 0 at the times when I am either positive or when the numerator here was 0. So all of this works. We don't want to include the -5 because that was when the denominator equals 0, and that would have a divide by 0 error. And then we would want to include all of this because this is positive, but we would not want to include the 6 because the 6 has a divide by 0 error. So in other words, the domain is going to be all x values. I'll write it as an interval first. It's going to be starting at -8, going until -5 with parentheses, and then picking up again after 6 and continuing till infinity. And if you wanted to write this using set builder notation, it would be a curly brace here with x values such that those x values are starting at -8 greater than or equal to x less than -5. That represents the same interval we just had above it. And, oh, we should never mind, not and, or, because it could be either. So we'll do or x values greater than 6. Good. Let's now take a look at question number 2. So for question number 2, we're trying to consider this function, and we're going to classify it as a polynomial, a rational, or a root function. Again, this is a polynomial because we have numbers times variables to positive exponents. And over here, we just have these unit blocks at the end. So this is a polynomial. And we can say because it follows the structure, because it follows a sub 0 plus a1x plus a2x squared plus a3x cubed plus ... Now notice again what this notation is if it feels a little awkward. A0 just simply means what is the coefficient for my x value that isn't there, right? In other words, that's the -3. That's what this A0 really means, is the -3. The A1 here would be the amount of x's, which in our example appears as -9. And we can see that the A2 then would be the amount of x squares or t squares, either one. A3, A4, we could have this as many times as that we wanted. Here it goes up to 4, but we could have it go up to 500. It really doesn't matter. Any of these are going to be considered polynomials, and they follow the same structure. Find the domain of f of t. Well, if we think to ourselves, are there any numbers you cannot multiply by themselves? You can multiply negatives by themselves, decimals, fractions, zeros, those all work out just fine. And since all we have here is a bunch of multiplication, some addition, and things being multiplied by themselves, there really isn't going to be any problem. So polynomials, in fact, always have a domain of -infinity to infinity. And that's because there isn't ever going to be a problem with multiplying something by itself. There's never going to be a problem with multiplying something by another number, and there's certainly not a problem with adding or subtracting. All right, let's take a look now at the next one. Determine whether the functions are even, odd, or neither, and then explain why. Well, remember that even functions are whenever you can take a negative x value and get the same thing as a positive x value. And it's because it resembles something like those U-shaped graphs we've been looking at. So for example, here, if I look at a negative x value like negative 4, it looks like I get a point on the graph right here. If I look at positive 4, I do not get that same height, right? There's not a value here. I would have maybe wanted there to be, but there is not. It's somewhere else. So that gives me enough reason to say this is not even. So I'll say not even. For odd values, that would be those that resemble kind of like an x cubed graph, something that looks like an S shape, but more specifically, we want it to be mirrored over the origin. So that means if I take some kind of negative value like negative 8, I'm looking for positive 8 to have that height, but just flipped to the top. So this height here is a negative 5. If I go over here to 8 and I look up, it looks like, oh, that's a positive 5. So it must be okay. Well, don't be so quick about that, because there are some other values, like if I look at, for example, this value here at negative 2, I would want the one at positive 2 to be the flip of that, made negative. So I would want it to be down here, and it's not. So even though there's one value that works, the entire function actually has to work for all values. So there's a missing value we would have wanted for it to be odd. So this is not odd. In other words, it is neither. For the next one, however, this would be an even function. Take a look, we can see it already. And if I take an x value of 2, I get a height near 2, and the negative 2 gets me a height near 2, and we can do this for every single one. An x value of 8 gets me a value of 8, so this over here would be an even function. Now when it comes to determining if a function is even or odd or neither using just your computational skills, we're really going to follow the exact same storyline. So we're going to start off with this idea of saying that we could consider some negative x values, and we really want to see if that causes this function to end up becoming the exact same thing it was, if it causes us to flip to a pure negative version of itself, or if it just becomes a scrambled up mess. So let's take a look at plugging in a negative x value here. If we plug in a negative x value, then we will get negative x to the fourth minus 3 times negative x plus 6. Oh, squared, there we are. Now if we think through this, what does it mean to do negative x times itself 4 times? Well, it's going to be a negative x times a negative x times a negative x times a negative x. And after we look at all these negatives times each other, negative times negative is a positive, negative times negative is a positive, so we really just end up getting the positive result of all of this. So we can think of this as being the same thing as what would happen if we just did a positive x to the fourth, because those negatives really don't play any role in this story. And similarly with this x squared, this negative x times itself is going to be the same as positive x times itself. So it's fine for us to look at this entire thing as just a negative 3 that will carry down times a positive x squared, because it's the same thing either way. And then plus 6. And after we take a look at this and we compare it to our original, we see it's actually the exact same thing. So plugging in negatives, that gets canceled out, in fact, by these even powers. So we can say that this f of negative x is actually the exact same thing as f of positive x, and that's the storyline we had already discussed for even functions. So this is enough justification for us to say this is an even function. All right, let's take a look at another one. So now determine if this one is even, odd, or neither. So we'll do the exact same thing. We're going to plug in a negative x value, and we're going to compare that to what we got with a positive x value. So now it's negative x to the 13th power minus x to the 4th power, minus negative x to the 4th power. And you can see I like plugging in the negative x's inside of parentheses, because that helps me to remember that I'm not simply doing negative times x to the 13th power. I'm doing negative x to the 13th power. Let me compare. If you are working through these problems and you write this for plugging in, this is actually incorrect, and you want to make a note to yourself that this is a mistake. And it's because this negative in front, according to order of operations, would be negative 1 times x to the 13th, which means we would want to do the exponents first and then make this negative at the end. Notice that with this version, we are multiplying negative x times itself many times, and we're not making anything negative at the end necessarily. We're letting the exponent grab the entire negative thing and repeat it, instead of here where we have it grab just the x and repeat it and tack on the negative afterwards. So now let's do negative x times itself 13 times. Well, we can logic through this without needing to write it down. This is an odd number of multiplies, which means that it's going to have, if we had 12, they would have canceled themselves out to positives, and that 13th would have then made it negative again. So this is the same thing as negative x to the 13th power. And then we can look at this next one and say negative x times itself 4 times would be positive x to the 4th power, and we'll carry this negative sign down. Okay, so now we take a look at this one and we compare it to the original, and we recognize that although the first term has now turned negative, it's turned into its opposite, the second term is the same, which means that as a whole, this is neither completely opposite nor completely the same, and so it's neither equal to f of x, nor is it equal to negative f of x. In other words, if this was the case, it would have been even, and that cannot be. And if this was the case, it would have been odd, and it's not. So this is in fact neither.